All right, where did I put that? Good grief. I can't find anything in here. I don't know. Oh, crap. This is the first of two videos about how computers do subtraction. And they do it in a very clever way, which really doesn't require us to come up with anything nearly as complicated as we did when we talked about the half adder and the adder in terms of doing addition. The method that we have, there are actually two different methods that we have for subtraction, will both rely mainly on addition. We will do subtraction by addition by representing our numbers in a particular way. Well, this first video is about something called the ones complement. And in the second lecture, we'll talk about something called the twos complement. These deal really with how we represent negative numbers within a binary system. And quite frankly, it's much more clever than I gave it credit for. You may have naive ideas about how they do deal with encoding negative numbers. I had ideas, and I was surprised about how it's really done. Okay, we're going to start on our subtractions by talking about some very, very special subtractions. First off, we'll start off with 2 to the nth power, which we represent in binary numbers with a 1 at the first, and then it will be followed by n zeros. Okay. Now, what I can do here is if I take this 2 to the nth power and I subtract 1 from it, this is going to leave me with just n ones. It's the binary equivalent to having like 999, etc. Where if you have all nines, if you just add 1 to it, then it'll get you up to 1 and all zeros. With binary numbers, you have all of these. If you have n ones, if you add 1 to it, it will give you 1 followed by n zeros. Okay. Now we're going to denote this by the letter B. I'm thinking of B as big. Okay. So we'll say B is equal to n ones in a row, however, for whatever value of n that we have. Okay, now let's take n equal to 4 now. When we take n equal to 4, our B becomes 1, 1, 1, 1, right? Just 4 ones, and I'll denote it to remind us this is binary. Now, let's do a subtraction from this. If I take this B and I subtract 0, 1, 0, 1 from it, which that is 5, right? If I take this, what I get is 1, 0, 1, 0. Okay. You can check this out yourself, converting to binary or whatnot, or converting it to decimal, doing your arithmetic there, doing it directly in binary. What I want you to notice is when our B is this special number, all ones, if we subtract a number from it that has the same number of bits, then all I'm doing is flipping the bits. So I can do my subtraction here just by flipping the bits around. Okay, so we will make use of this when we do our more general subtraction. All right, so what we want to do here is to define the ones complement. And so let's start off. I'm just having b being a number, right? And I'm going to be interested in 0, 1, 2, 3, 4, 5, 6, 7. I represent this as binary. 0, and again, with 4 bits, 0 is represented as 0, 0, 0, 0. 1 is represented as 0, 0, 0, 1. 2 is represented as 0, 0, 1, 0, and so forth. You can look down the line. We're just counting our way up in binary, just kind of clicking over each time to add a new one here. But we're going to stop here at 7. Well, and it looks wasteful because we still have that 0 at the top, but that 0 is being held for a special purpose. Okay. And so we go over to this other column, which I have capital B minus little b. Now the capital B stands for all ones, right? And so like my capital D minus 0, it gives me all ones. My capital B minus 1 is 1, 1, 1, 0, and so forth. And as we go down, we maintain that 1 in the first bit, the most significant bit, but we lose them down in the other bits till we get to 7, when that's just 1, 0, 0, 0. Now, what we kind of do here is we think of this column, the b minus little b, as being the negative of what we have in the middle column, okay, or the negative of the first column. So 1, 1, 1, 1, we're thinking of it as being negative 0, okay, which is weird, okay, if you come from thinking about math, but this is the way computers deal with things. We'll get down here, we think of 1, 0, 1, 1 as being negative 4, okay? And, but we think of it that way, but we call this last column the ones complement, okay? So you're taking the ones complement of a number, and you will have to have a set word length, right? Here our word length is n equal 4, and so the ones complement depends on the word length, and it depends on well, the number that you're dealing with. Okay, so let's we'll in the remainder of the lecture we'll see how this is used. All right, let's take a look at what happens when I take 3 plus b minus 7. Okay, 3 plus the ones complement of 7. This will give me 0, 0, 1, 1 plus 1, 0, 0, 0. When I add them together, this gives me 1, 0, 1, 1. Okay. Now 1, 0, 1, 1 is, if you look in our table, is just the ones complement of 0, 1, 0, 0. Okay. Or you don't even have to look at the table. You can just kind of do that in your head. And that is b1 minus 4, or excuse me, b minus 4. And if we're thinking of our ones complement as the negative of 4, we get right here that 3 minus 7 is negative 4. Okay, and you think, well, it's beautiful, it's simple, I didn't know everything was that simple. Well, let's look at another example. Okay, so here let's take 7 plus b minus 3. And again, if we're thinking of b minus 3 as negative 3, we're going to expect to get 4 out of this. So let's take a look. 7 is 0, 1, 1, 1. The ones complement of 3 is 1, 1, 0, 0. So when we add these together on a 4-bit register, what we'll get is 0, 0, 1, 1 with a carry of 1, okay? Because it busts us out of that 4-bit structure. But let's not lose heart. What that carry of 1 is takes us out to that next bit. It'll be a 1 in the 5th bit, which is a 2 to the 4th power, plus this in binary, which is 3. Okay, so what I can do here is say, okay, the 2 to the 4th is b, my all ones, plus 0, 0, 0, 1 in binary, then plus the 3 out at the end. Okay, and now I can combine my 0, 0, 0, 1 with my 0, 0, 1, 1, and that'll give me 0, 1, 0, 0. So I have this b on one side and that b on the other. If I subtract them out, then, hey, I have 7 minus 3 is equal to 0, 1, 0, 0, which is 4, just as pretty as you please. But what we've done here is we've taken the extra 1 that was carried out and we've added it to the bottom to get there. That means we're going to have to change our addition a little bit. So if you make a decision that the way you're going to do your subtraction or the way you're going to encode your negative numbers is by ones complement, what you have to do is to modify your addition algorithm. Okay, you put your addition algorithm where you have your second number, if you know that that's a negative because it has a leading 1 in that most significant column. Okay, so you're subtracting by adding that way. Then you do your addition. Okay, and you'll have a carry. Your carry will either be 0 or 1, and so you'll just take whatever your first sum was down to this stage, okay, the next stage, and roll the carry, whether it was a 0 or whether it was a 1, you roll it back here and you do your addition again. Now, this addition, it's going to be a much cheaper addition than what you did the first time, but you're still having to add an extra step into it. Okay, there are some machines that still do this. It's still out there. But there is another way that's more commonly used, which is called the twos complement, which we will talk about in another lecture. Well, thank you for sticking around this long to listen to this. We'll conclude in our next lecture when we learn about the twos complement. If you enjoyed this, please like, and you might even want to subscribe to the channel. Thank you very much. Yeah, who is it? No, I'm not doing anything. Come on in.